Hey everybody, welcome back to this video series where we are trying to build a Minecraft clone with JavaScript and Three.js. So in this sixth video of the series, we're going to work on infinite terrain generation. I'm going to kind of explain what that means, what kind of approach we're going to take. We'll be looking at the actual Minecraft game to see how they do it. Then we'll try and mimic that with our own game. So where we had left off, we had implemented collision detection, and now we can generate a world and we can walk around it. But one issue is that our world has finite bounds. So as you can see, I'm kind of at the edge of the world here, and I can go over here, and we're at the edge of the world there. And Minecraft is really about exploration. It's about this, infinite or nearly infinite world that you can explore and build and create in. If I back out right now to the third-person camera, you can see this is basically what we have to work with here. This is the area we have to explore, and this really isn't very big. Now you're thinking, why not just make the world bigger? And the issue is really two issues. The first is that we start to run out of memory. So we can only hold so much of the world data in memory before we're going to run out of memory. So that's one issue. And the other issue is that if we try and generate the entire world at once, it's going to take a really long time to load. So if you can think, instead of 128 by 128 blocks, we had 10,000 by 10,000, that's going to take forever to load all that data. And it's probably going to be pretty slow because we're going to have, millions upon millions of blocks on the screen. And even a really powerful computer is still going to have a tough time rendering all of that. So how we're going to fix this issue is going to implement something called chunking. And this is what the actual Minecraft game uses. So I thought we would take a look at the real Minecraft game and try and get a sense of how they're achieving this infinite terrain. So I'm playing in the Java edition on Mac. I'm in creative mode, so I can just fly around here. Now, there's two things that you'll notice. The first is that the world really never seems to end. I can just keep flying and flying, and there's just more and more to explore. Now, we kind of know from intuition that it's not rendering this infinite world because my computer would just grind to a halt. So what it's using is something called chunking. Now, I can go into the options and go into video settings, and you can actually see there's two settings here for the render distance, which is set to 10 chunks right now, and the simulation distance, which is set to 12 chunks. With render distance, you can assume that's kind of how far we can see, but you can also kind of simulate what's happening in the world a little bit beyond what the player can see. So we're just going to have one control just for the render distance, since we're not really simulating anything yet. So I'm going to set this to something really small. Let's say 4 chunks. And immediately you can see the fog is much closer to the player. There's really not a whole lot you can see. So if you're running on a really crappy computer, this is probably what you'd have to set it to. So what happens if we set this to some really large value, some really large render distance? So going here and video settings. So I'm going to set this to 20. Now pay very close attention when I come out of the options, because you actually see the chunks being generated in real time. It's going to be really quick. All right, here we go. So you can see those blocks appearing as I'm just sitting here. And it's kind of happening asynchronously. It's happening in the background. So I can still kind of float around the world. I can keep moving, and it's really not slowing anything down. These chunks just keep appearing. So this is exactly the system that we're going to replicate in our Minecraft game. We're going to render a certain amount of chunks around the player based on some render distance that we set. And then as the player moves around the world, we're going to create new chunks. If the player gets to the edge of a new chunk and crosses over, then there's some other chunk in the distance that should then appear. And likewise, if a chunk is beyond the render distance, we want to remove that from memory. So we only have so many chunks in memory at one time, and we're not going to run out of memory. So there's a whole dynamic terrain generation process that we need to figure out. So we're going to be splitting our terrain generation logic into two separate classes, world and worldChunk. So worldChunk is going to handle all of the actual terrain generation logic. We currently have that in the world class, so we'll need to move all that code into worldChunk. And then world is going to be managing all of the chunks. So we'll need to create a world that can be actually composed of multiple chunks. We'll need to be able to handle the physics. So when the player moves from chunk to chunk, the physics is seamless. And we'll also need to handle the actual creation in some sort of asynchronous way so that when we're creating new chunks, it's not completely slowing down the game. So since we already have our terrain generation logic in our world class here, we're just going to rename this to WorldChunk. Then we'll create a new file to contain the world class, which will handle our chunk management. So I'm going to go ahead and hit F2 on here, rename this to WorldChunk. And let's go ahead and also update the file name to be WorldChunk as well. And then I'll create a new file called world. Now I've created just a basic class here, and see we're just importing the Three.js library. And then we're importing our WorldChunk class. And then I have a world class here that extends from three.group. So this is going to be containing a bunch of chunks, which are their own little Three.js object. So our world is really just a group of these objects. And then the first parameter I have in the constructor here is a seed value. So we can pass that seed into the train generation logic and create different types of worlds. So the next thing that I'm going to do here is go into our WorldChunk class, and I'm going to move these parameters to the world class. So we'll just put those at the top here. And we'll pass these parameters into each chunk when we're instantiating it. And then we also want to pull out the size, and we're going to rename this as well. So we'll pass in the size, and then for our world, we're actually going to call this chunk size. So there's kind of two different concepts of size here. There's the size of our world, so how many chunks wide by how many chunks deep. And there's also the size of an actual chunk, so how many blocks are in one chunk of our world. So we need to pass those parameters that we pulled out into the chunk. So let's go back into here, and we'll create a new argument called params, and then we'll say this.params equals params. So we're going to need to update our main file here and our UI file to reflect the changes that we just made. So in our UI file here, for our world size parameters, this is no longer called size, this is called chunk size. So in our main file, you can remember that when we're creating our world, we have this generate method that we're calling at the very beginning to just generate all the blocks in the world. So we need to add that method to our world. So below our constructor, we'll go down here and define a function called generate. And then we're just going to start with a fairly basic implementation here. Our world is only going to have one chunk in it. So we'll just create one chunk. We'll do a new world chunk. And then we'll pass in the chunk size and then the parameters that we've pulled up to our world class. Then we'll call generate on that chunk. That will generate all the blocks for that chunk, all of the mesh data. And then we'll add the chunk to our world here. So we've kind of finished abstracting our world here. We have all of our train generation logic in WorldChunk. We have our chunk management in our new world class. We define our chunk size in there, our chunk parameters. And we're generating our world by just creating one single chunk, and then we're adding it to our world. So we kind of have enough here. We can go to the browser and test this out and see what we have. So right away, I can see that we're getting an error here in our physics code. World getBlock is not a function. So I can see this is being called in the broad phase of our physics code. And this is because in our old world code, which is now WorldChunk, we had a method called getBlock, where we could get the block at a particular location and see if the player should collide with that or not. So we need to define something similar in our world class. So let's start with kind of a naive basic implementation, and then we'll build on top of that as we go. So I've defined a little skeleton here for our getBlock function on our world class. So you can see it's very similar to the getBlock function that we had before. So for now, since our world just consists of one chunk and we're storing it in the chunk property on our class, all we're going to do is return this.chunk getBlock, and we'll pass in the XYZ coordinates. So eventually when our world is comprised of just more than one chunk, we're going to actually have to figure out which chunk to pull the block from. But for now, we're keeping things simple. We're just worrying about one chunk. So we're just going to get that chunk's blocks. So with our getBlock method now defined, I expect that everything should work now. So let's go back to the browser and check it out. And sure enough, we have a world that looks just exactly like what we had before, which is what we expected, since we only have one chunk. So I promise this will get more interesting in a few minutes here. So let's quickly just test things out. Let's go into first person mode. Looks like my guy's falling, so let me refresh here. And if I jump around the world here, we can see that our physics is still working. And it looks like everything is kind of working as expected. So really our world class is just acting as a pass-through right now to the WorldChunk class. So it's time that we added a few more chunks in so we can start generating that infinite world and make it more interesting. So let's blow away our code and our generate method here. We don't really want to generate a single chunk. We want to generate a whole bunch of them. So let's delete this, and I'm going to turn this into a double for loop. So let's loop over the X and Z coordinates. And I want to create a world that's 3 by 3 blocks. So I'll go from -1 to 1 in the X direction and -1 to 1 in the Z direction. So for each set of XZ coordinates in this loop, I want to go ahead and create a new chunk. So we'll do new worldChunk. Then like before, we'll pass in the chunk size and the params. Now, one thing that we need to do differently when creating multiple chunks is we need to set the position of the chunk, the origin of it. So we'll do chunk position set. So we'll take our X value here that we're iterating over, and then we'll multiply that by the width of the chunk. So you can think of our chunks, let's see here, they're 64 blocks wide. So if I'm moving along in the X direction, I'm creating chunk after chunk after chunk. I'm going to place one down, then I'm going to move 64 blocks. I'm going to place the next one, move 64 blocks, place another one. So for the Z-axis, I'll do something similar. We'll also multiply our Z variable that we're iterating over here by the chunk width. And then finally, we're going to call generate on the chunk, and then we'll add the chunk to our world. Now, one thing that we need to be careful of when we're removing old chunks from the scene is that we need to dispose of those unused resources. So if we're looking at the documentation for the instance mesh class here, you can see that there's a dispose method defined, and this frees up GPU-related resources allocated by this instance. Call this method whenever this instance is no longer used in your app. So we are using instance mesh quite heavily, so we need to make sure that we call this anytime when we're removing a chunk from the world. So at the very bottom of our WorldChunk class here, I'm going to create a new method called dispose instances. So I'm going to traverse over all of the children of our WorldChunk here, which is the instance meshes for each block type. If the object has a dispose method defined, then we want to make sure we call that method. And then finally, just to be super explicit, we will clear all of the child objects. Now, back in our world, we also need to define a dispose method here. So we'll call this dispose chunks. So we'll do this traverse. So these are really chunks in this case. So if chunk.disposed instances exists, then we'll go ahead and call that. Now at the very top of our generate method here, each time we regenerate the world, let's go ahead and be safe. Let's just dispose of all of the chunks that may already be existing. So one last thing I forgot to add in here is that we actually want to also keep these X and Z coordinates. These are really useful for keeping track of kind of the X and Z like array index. You can kind of think of it like that. You can't really use the position because this is kind of taking into account the actual size of the chunk. So one easy way to do that is just to store that information in user data. So we'll just store the X and Z coordinates there, and we're not going to use this right away, but we're going to be using this later on. Now going down to our getBlock code, we no longer have this .chunk. We need to be able to look up the chunk at a certain position, but for now, we're not going to worry about the physics. So let's just have this return null, and we'll implement this later. So going back to the browser now, I expect that we're going to have a world with multiple chunks, and that is what we have. So if I zoom out here, we can see that as expected, we have this kind of 2D array of chunks here. So we have 1, 2, 3 in the X direction, 1, 2, 3 in the Z direction for a total of 9 chunks. Now, one issue you might notice is that every chunk is exactly the same. So in our code where we're doing the sort of the terrain generation, each block knows its position relative to the origin of the chunk. So we need to add the world position of each chunk to the world generation code so that we get more of a seamless terrain here. We're not just duplicating the same thing across each chunk. So this is actually really simple to do, just requires a couple updates. So the X, Y, and Z position here, so you can see these range from 0 to the width of the chunk. So all we need to do is add the position of the chunk to get the absolute position of a block within the world. So we'll do this .position.x plus x, and then we'll add the chunk position to each of these. Now we did that for generate resources, so let's do the same thing for the terrain generation as well. So let's update where we're calculating the simplex noise here. Change this to this position.x plus x, and this .position.z plus z. Now those should be the only two places we need to update to get the absolute position of the block. So let's go back to our world here, and we can see that we now have this seamless terrain. We're not just kind of copy pasta each chunk over and over again. But let's go ahead and have some fun. Let's play with the terrain parameters here and kind of make sure that all of our chunks are connecting together seamlessly. So if I increase the scale, you can see that we have these, larger mountains, these terrain features that are spanning across multiple chunks. I can increase the magnitude, or I can decrease the magnitude. You also notice that our terrain generation has slowed down quite a bit since we're having to create multiple chunks. And I can also tweak the seed here so I can get just different types of worlds. So this is really cool, but one issue that we're having right now is, say I go into first person view and reset this, you can see that our player is just falling through the world. This is because we haven't implemented getBlock. So the physics has no way of knowing where a particular block is within the world. So we're going to have to go and implement that next to get our physics working again and have our player colliding with the terrain. So in order to get our physics code to work again, we need to implement two separate functions. Now, the first is going to take our player position, and it's going to convert that to a set of chunk coordinates and block coordinates within that chunk. So the chunk coordinates are like the x equals, -2, -1, 1, 0, 1. That's what we're storing in user data. And then the block coordinates is what we've been using before, and that will be relative to the chunk itself. The second function that we're going to implement is called getChunk, and all that we'll need to do is we pass in the coordinates of our player, and that will return the actual worldChunk object that the player is currently inside of. So I've outlined the two functions that we'll be creating here. First is worldToChunkCoordinates. So this will return the coordinates of the block at the world XYZ position. So this will actually return an object that contains two properties here. So chunk is the coordinates of the chunk containing the block. And when I mean chunk coordinates, I mean those that we're storing in user data. And block is going to be the XYZ coordinates of the block relative to the chunk. So those will range from 0 to the width of the chunk, or the height of the chunk in case of the y-axis. And for our second function here, we'll return the worldChunk object at the specified chunk coordinates. So we pass in the X and Z coordinates of the chunk, and we'll return the WorldChunk object back. If no object exists, or no chunk exists at that location, then we'll just return null. So starting with world2chunk coordinates, let's work on the implementation for that. So first we'll need to calculate the chunk coordinates. So we'll call this ChunkCoords. So this is going to be an object. So for the X coordinate, so we're going to take the floor of the X position that we're passing in here. So this is the, the player world position. And then we'll divide that by the width of the chunk. And then we'll do the same thing for the Z, floor of Z divided by chunk size width. So let's say our player is at an X position of 100 or a Z position of 100. So if we take 100 divided by, so our chunk width up here is 64. So 100 divided by 64 is 1 point something. So we'll take the floor of that. So the chunk coordinates would be X equal to 1 and Z equals 1. So calculating the block coordinates isn't too much harder. Let's go ahead and define another object called blockCoords. So to calculate this, we'll take the world position, the X position that we pass in here, and then we need to subtract the origin of the chunk, the world position of the chunk's origin. So we can calculate that pretty easily by just taking the chunk size width. So in case that's 64 blocks, and then we'll multiply that by our ChunkCoords. So let's say our ChunkCoords, the X coordinate is 1, the chunk size width is 64. So the origin of our chunk is 64 blocks from the complete origin of the world, the absolute origin of the world. So if we're trying to get the coordinates of the block relative to that chunk, let's say our player is at 100, we'll subtract 64. So the block position relative to the chunk is going to be X of 36, 100 minus 64. We don't do any chunking along the Y-axis, so we'll just pass in the absolute world position, the Y position here. And then the Z is very similar to the X. Multiply the width by the Z chunk chord. And then we'll just return our chunk chords and our block chords. And we need to return or set the names of these properties. So I'll call this one chunk and this one block, just to make it a bit more shorthand. Now for getChunk, we're going to make use of this user data that we set here. So remember the kind of the X and Z indices of our chunks. We're storing that in user data in this object here as X and Z. So to find the chunk at those X and Z coordinates, we're going to search through all of the children. So we'll loop over each chunk. So we'll find the chunk where the user data X is equal to chunk X and user data Z is equal to chunk Z. Now there's probably a bit more efficient way of doing this. You could use some kind of lookup table, but in reality, we're really not going to have a lot of chunks spawned at any one time. So it's not too intensive to use a loop here and just iterating over them and finding the one that we need. So now that we have these two functions defined, we can finally go and implement the getBlock function here on our world. So first thing that we'll do is we'll get the coordinates from our world2chunk coordinates. So just call world2chunk coordinates, pass in the X, Y, and Z position, the absolute position of the block. Then we also need to get the chunk. So we'll do getChunk. Then we need to pass in the chunk coordinates here. So we'll do chords chunk.x, chords chunk.z. So we're utilizing the coordinates that we obtained in this line here, and then we're passing them to get the chunk. So if the chunk exists, then we want to get the block inside of that chunk. So we'll return chunk getBlock. Now the X, Y, and Z here are relative to the origin of the chunk. So we're going to use the other part of our coordinates here. So we'll do chords block.x, chords block.y, chords block.z. So we're passing in the relative position of the block relative to the chunk. So you can see this is all kind of coming together now. And of course, if no chunk exists at that location, then we'll just give up hope. We'll just return null here. And one other issue I ran into here is I forgot to clear the chunks when we're disposing. So we'll definitely need this anytime we're changing the parameters. We're going to need to clear the existing chunk objects. So if we go into the browser now, let's turn the scale up a bit, and we'll turn the magnitude down to make this a bit more walkable. And now I expect to be able to walk across this entire terrain without falling through. So let me get my player moving here. So you can see I move over here. And I know I'm already on another chunk by now. And I'm colliding into the terrain as expected. So there we have it. Our physics is now working across all of the chunks. We have the seamless experience where our player can walk between chunks. And the collision detection works as expected. So let's turn up the magnitude a little bit here. Make it a bit more varied in terms of terrain. And reset the player position. And yeah, there we have it. We can scale up and down these mountains. So all of that is now working as expected. Super great. So to quick recap where we're at here, we've refactored our world generation code into two separate classes, world and worldChunk. So worldChunk contains our terrain and resource generation rules, while world contains the chunk management code. And we've also shown that we can create a world composed of multiple chunks, and the player is able to seamlessly walk between those chunks without issues. And our terrain generation is also kind of seamlessly moving from chunk to chunk. So the player really has no idea when one chunk ends and when a new chunk begins. So the next thing that we need to work on now is kind of the crux of this whole thing is that as our player moves around this world, we need to start generating chunks ahead of where the player is moving. As a player gets close to maybe where a certain chunk should be but doesn't exist yet, we're going to have to create that chunk. And likewise, if a player exceeds some certain distance from another chunk, that chunk isn't going to be visible anymore. So there's no need to have it hanging around. We're going to go and remove that chunk. So as the player moves around this world, we'll just be adding and removing chunks dynamically. The player will never know what's happening, but it will give this impression of the seamless, infinite world that we kind of expect in Minecraft. So in order to implement our infinite terrain generation and have chunks dynamically being created and removed from the scene, there's 4 different things that we're going to need to do here. And I've encapsulated them in this update method, which I have defined on our world class. So first thing is we pass in our player. And this is going to be called basically every frame, every time our player moves, we need to determine if there's chunks that need to be created and rendered, or if there's chunks that need to be removed. So how does this update process work? So first we need to find the visible chunks based on the player's current position. So these are the chunks that the player should be seeing. So we'll get the coordinates of those, and we'll compare with the current set of chunks that are currently in the world. And then we'll go through and we'll remove chunks that should no longer be visible. So if there's some chunks that are currently in the world and they're not included in this visible chunks list, then those need to be removed. And likewise, if we look at the set of visible chunks and we find some that aren't currently in our world, then we need to add those chunks. So it's kind of just getting these 2 sets of chunks, the ones that should be there, the ones that are currently there, and just comparing those 2 sets to determine which chunks need to be removed and which ones should be added. So before we get into all this logic, let's just go into our main file here, go down into our game loop, which is right here. Then right after we update our physics, let's just call world update player. And this will just update those set of chunks that are in view and which ones are currently in the world. So let's start by implementing this first one here, finding the visible chunks based on the player's current position. So I've added just an outline of this method. So it's going to return an array containing the coordinates of the chunks that are currently visible to the player. So we'll pass in the player. So we'll basically use the player's position. And then we're going to turn an array here of X and Z coordinates, which map to, see if I can find it, map to these coordinates that we're storing in the user data. So the first thing that we need to do is we need to get the chunk that the player currently is inside of. So we'll define a new variable called chords, and we'll call worldToChunkCoordinates. Then we're going to pass in the player position here. Now from these chords, I'm really just interested in the X and Z position of the chunk. So to make things a bit more readable, we'll just pull those variables out. And now we're ready to go ahead and define that array of visible chunks, that array of coordinates. So we need to define one more variable at the top of our world class. Let's go ahead and do that now. We'll scroll up here. So I've defined a new variable called drawDistance. So this is basically how many chunks away from the player do we need to render. So you can think of the player being on a chunk by itself. And if we just draw that one chunk, that's a drawDistance of 0. Now, if we were to draw all the chunks surrounding that one chunk that the player is on, that's a drawDistance of 1. If we were to draw another layer of chunks around that, that's a drawDistance of 2. So you can kind of think about it like an onion with different layers with the player at the center. So we'll set this to 1 to start with. We don't want to render too much stuff and slow us down, but we'll adjust this kind of based on the performance of the game once we get to that point. So starting with 1 here, let's go back down to our getVisibleChunks function. And we need to basically loop over the x-axis and the z-axis and sum up all of those coordinates. So what we need to do here is to loop over the x-axis. So we'll let x equal, so we'll take chunk x minus the drawDistance. And then we want to go until chunk x plus the drawDistance and x plus plus. I'm going to hide the sidebar here, give us a bit more room to work with. And then all we need to do inside of here is, for our visible chunks, we'll push on a new object containing the X and Z coordinates. And when we're done here, we should have an array containing the coordinates of all those different chunks that need to be drawn. So back in our update method, we will create a new variable. We'll say visible chunks is equal to getVisibleChunks. Then let's pass in the player to that. Now we'll do a bit of debugging at each step of the process here, make sure that we're getting the right result as we go. So let's log visible chunks to the console here. Now in our browser here, it looks like we're not actually getting things printed to the console. So it looks like I screwed something up. Let's go back to the code. And I already debugged this a bit beforehand, but I made a mistake right here, destructuring this. So chunk contains the X and Z properties. So those don't really map to anything here. So really what I need to set this to, let's just do 2 separate variables. This will be chords.chunk.x and then chunk z equals chords.chunk.z. So back in our browser now, we can now see that we're getting an array of 9 elements. So you can see that we're getting the coordinates that we expect here. The player is in chunk 0, 0, x0, z0. So it's getting all the chunks from x -1, z -1, all the way to x1, z1. So I'm going to move my player to the x1, z1 chunk. So I'm going to go right here, and then we'll just clear this out. And now you can see that the visible chunks is now changed. So it's no longer x -1, z -1. It's ranging from x0, z0 to x2, z2, which is what we would expect, because our player is currently in this chunk right now, and our draw distance is set to 1. So if we go 1 either side of x equals 1, that's x of 0 and 2. And draw distance either side of z equals 1 is going to be z equals 0 and z equals 2. So our getVisibleChunks is working as expected. So we can now move on to the next part, which is getting the chunks that need to be added. So the next function we're defining here is called getChunksToAdd. So we're going to take the visible chunks, that array that we just found. We're going to pass it in as the parameter here. So this returns an array of the coordinates of the chunks that are not yet loaded and need to be added to the scene. So we're basically going to take each set of coordinates in this array here, and we're going to compare it against the chunks that are currently loaded and see if there's any chunks that aren't in the scene yet that need to be added. So how I'm going to approach this is I'm going to filter down the visible chunks to those not already in the world. So I'm going to apply a filter to our visible chunks. So I'm going to create a variable here called chunk exists. So we're going to determine if these chunk coordinates are within the currently loaded chunks. So we'll loop through all of the children on our world. So first I'm going to do a quick map here. So we're going to return the user data of the chunk, which contains the x and z coordinates. And within the chunks currently in our scene, I want to find. So the argument passed in here, since we mapped this to the user data, we're going to get the x and z coordinates. Basically, I want to find anything where the chunk x coordinate is equal to the x coordinate and the chunk z coordinate is equal to the z coordinate here. So if the visible chunk x and z coordinates are found within the children, the currently loaded chunks, then we know that that chunk exists. But we want to filter this down. We want to get the chunks that need to be added. So we want to find the chunks that don't exist. Filter keeps all the things where we return true on those elements. So let's keep the chunks that do not currently exist. So we'll negate that here. Back in our update method here, let's replace this comment. Let's create a variable called ChunksToAdd. We'll call getChunksToAdd. Then we'll pass in the visible chunks here. And then we'll log ChunksToAdd to the console. See, now to make this a little bit easier to tell what's going on here, I'm going to add some labels to the console. So I'll just print what each array is prior to printing the array. So let's go to the browser now and see if everything is working correctly. So to make things a bit easier to see here, I've added a bit of a gap between the chunks so we can see where one stops and the next one begins. I've also made the chunks a bit smaller, so don't have to walk around so far to move to the next chunk. So right away, with my player in the center chunk, you can see that our visible array is kind of what we had before, and ChunksToAdd is an empty array. So since all of the chunks that are visible are already loaded into the world, then there's nothing else that needs to be added. So let's move our player to one of these corner chunks, and then we'll expect that ChunksToAdd should have something in it because chunks that should be visible aren't all loaded into the world. So I've moved the player to the x1, z1 chunk, and just so you can kind of get a reference here, positive z is to the right side of the screen, and positive x is to the top of the screen. So looking at visible here, we can see that it ranges from x0 to x2 and z0 to z2. And that makes sense because our player is sitting in that middle chunk x1, z1. Now, ChunksToAdd now is an array with 5 elements inside of it. So let's take a look at those and see how it compares to the visible chunks. Kind of working from the bottom here, to2chunk needs to be added. So if we think about it, that's the chunk to the upper right of the player. And that makes sense because that one isn't visible yet. And the one above the player would be the 2.1 chunk. So we can see that one here. The one to the right of the player would be the 1.2 chunk. And then to the upper left of the player would be the x2 z0 chunk. And then the one kind of to the bottom and to the right of the player would be this x0 z2 chunk. I might have screwed that up trying to keep the axes straight in my head, but one thing to note there is that the chunks that are already loaded are not included in this. So that would be the, let's see if positive z is in that direction. So this would be z0 x1. That's this chunk here. So that one's already loaded. And likewise, the x0 z1 chunk is loaded. And those are not in ChunksToAdd. So that makes sense. Also, the x1 z1 chunk that the player is currently on, that one's already loaded, so that doesn't show up in the list. And also the x0 z0 chunk, that is also loaded, and that does not show up in ChunksToAdd. So if you kind of compare those two arrays, it all makes sense that the chunks that need to be added are the ones that are visible but are not currently loaded in the world. So the next step is to find out which ones need to be removed from the scene. So if the player is on this upper right chunk here, then all these chunks, so the one on the very far left here, the one below that, one below that, one to the right, one to the right, those chunks would all need to be removed from the scene because they're further than one chunk away from the player. They're further than the draw distance. So back in our code here in our world class, I've added a new function, and that's right below our getChunksToAdd function. And that is the removeUnusedChunks function. It's actually going to do two things. It's going to find the chunks that need to be removed, and it's also going to go ahead and just remove them immediately. Now, for testing, we're not going to remove the chunks right away. We're going to add that in later, but we'll return the list of chunks that need to be removed. So then we can also print that array as well and kind of see if that matches up with what we were talking about before. Now, the logic in removeUnusedChunks is kind of the opposite of what we did for the getChunksToAdd function. So in this one, we wanted to look at all the visible chunks and filter down those that already exist and remove those. So any that should be visible but aren't already in the scene, those are the ones that we need to add. So we're going to kind of flip that now. We're going to look at all of the chunks that are currently in the scene but should not be visible. And those are the ones that we need to remove. So I'm actually just going to copy this function and paste it in here. And really all I need to do is just flip visible chunks with this .children. So this is our visible chunks array that we pass in, obviously, and this .children, those are the chunks that are in the scene. Now we do need to tweak this slightly here because the map function we were calling on children before to get that user data, the XC positions. So now we need to move that up here. So XC is equal to chunk user data. Can get rid of this map here. And visible chunks is an array of XZ positions. So we'll just call this visible chunk and we'll place this here. So we're comparing the XZ position of the chunk object in the scene and comparing that to the XZ coordinates of the visible chunk. Now moving back up to our update function, let's go ahead and remove this comment here. And similar to what we've been doing before, now we'll go back to the scenario that we were looking at before where the player was in the X1, Z1 chunk. And remember we were kind of talking about which chunks we expected to be removed. So we'll go and look at the chunks to remove array and make sure it contains all the coordinates of the chunks that we expected. All right, so we have our player in the X1, Z1 chunk. Remember that positive Z is to the right, positive X is up. If we go to the left here, we expect that, this chunk to be gone, the chunk below that, this chunk down here, and this one and this one. So moving to the left, that's decreasing Z. So this chunk here is X1, Z minus 1. And if we look at our chunks to remove here, you can see that that is this chunk here. Now, moving down, that is decreasing our x value. So we go from x1z minus 1 to x0z minus 1. That's this chunk here. So we want to remove that one because it's further than one chunk from the player. And moving down one more to this chunk, that's the x minus 1, z minus 1. So that one's there. And now we're moving to the right, increasing z. It's going to be x minus 1, z0. And moving to the right again, x minus 1, z1. So we expect these 5 chunks along the edges to be removed. So we are getting the results that we expect. So this is really all the information that we need in order to dynamically add and remove chunks from our world. So we know which chunks need to be added to the world, and we know which chunks need to be removed from the world. So now we can go ahead and actually write that logic that will spawn new chunks and remove the old ones. So first I'm going to update our removeUnusedChunks function here. So we can get rid of that map. We don't need that anymore. And instead of returning this, we're just going to assign this to a variable, chunks to remove. And then we're going to loop over these here. So first we'll call chunk dispose instances. So that will clear all the instance meshes for that chunk. And then we need to remove the chunk from the world. So we're in the world class, so we remove it from this. And then let's just do a quick log statement here so we know which chunk is being removed. All right, so that will remove the chunks from the world. And then we can go back up to our update function here. And since this doesn't return anything anymore, we can just delete that. I'm also going to delete these other log statements. We don't need these anymore since we know that's all working. So let's test this code out quick before we work on generating new chunks. So for the purposes of this demo, I have set the terrain to be completely flat, make it a bit easier to see. So you can see our player is currently kind of pointing upwards. So I'm just going to walk in that direction. And then we expect when the player gets to the chunk up here above the player, that these chunks at the bottom here, those are going to be removed because they're further than one chunk away from the player. So I'm just going to walk in this direction. And in the console here, you can see right away that the chunks at the kind of the z equals 1 mark were removed. So let's go back to the third person view. And sure enough, you can see that those chunks have been removed from the world. Now, if I go to the chunk to the left of the player, we expect these chunks on the right side of the screen, those are going to go away. So if I move to the left here, we saw 2 more chunks removed. And sure enough, those 2 chunks that were once over here are now gone. We can see that our removeChunks function is working. So now it's working on adding new chunks. So below our removeUnusedChunks function, I've defined a new function here called generateChunk. So this will generate a chunk at these coordinates here. So we'll pass in the XZ coordinates of the chunk. So all we need to do here is let's go back up to our generate function. So this is where we kind of initially generate the entire world. So we can just grab this code in the middle here. So this is exactly what we need. And I'll just paste it in here. And this 1.01 factor, that's that little hack I did. So we get a little gap between the chunks. So once we verify this is all working, we're going to remove that. So you can ignore that really. And I want a log when I'm adding a chunk. So we'll copy this log statement. All right, so we're creating a new chunk, passing in the chunk size, the parameters. We're setting the position of the chunk, setting the user data. We're actually generating the mesh data here. Then we're adding it to the world. So pretty straightforward. That's what we've been doing already. But this should be the final piece we need for our dynamic terrain generation. So the final thing we need to do is tie this into our update function. So up here, we'll remove this. So all we need to do is loop over each chunk in ChunksToAdd, and then we will call generateChunk. So we can just do chunk.x, chunk.z. There we go. That's all we need. So first we'll remove the chunks, then we'll add in the new ones. All right, so now I should be able to just walk in any direction now, and chunks should be generated ahead of me. And we'll also see some output in the console as well to verify that's working. So as I walk in this direction, you can see that chunk was generated. Here's the dividing line here. So as I cross this, we should see new chunks pop into view. Boop. There we go. If I go to the right here, another chunk pops into view. And then if I back up, so I'm back into the previous chunk, we should see that chunk in the distance removed. And that is the case. So if I pop back into third person view, so if I move the player forward here, and then go back out, you can see that chunks over here, those are all removed, and we added some chunks over here. So infinite terrain generation is working. Super awesome. All we need to do is remove that little that multiplier we added in. Now as the player walks in the world, we no longer have those seams between chunks. So that is really cool. This is one thing I love about doing this procedural generation stuff is, I just have this infinite world being generated in front of me. I can keep walking and something new is always going to be created. So that's what I really like about this project. Further test this one little bit, let's increase our draw distance. So let's change this to 2 instead of 1. So I actually added those gaps back in to demonstrate an issue here. So the draw distance is set to 2, but we're only rendering 1 chunk around the player. That's because when we're initially generating the world, we're not taking into account the draw distance. So going back into the code here, I forgot to update these. So these should be draw distance instead of 1s. So we'll update that. And now when we go back in, we can see that instead of generating 9 chunks here, we're generating, let's see, that would be 19. We're generating 25 chunks total. So let's move my player forward here. And you can see that a whole bunch more chunks are being generated. One thing you also notice is that as these chunks are being generated, the game kind of stutters a little bit. So we're going to fix that issue later. We're going to asynchronously generate chunks kind of in this queue. So we'll do 1 chunk generating at a time. So we're not just blasting the CPU trying to generate a bunch of chunks at once. So before we jump into that, there's just a couple tweaks I wanted to make to the UI here and these controls. If we try and modify the chunk size in real time, so when the game is running, it kind of works, but typically you run into some issues doing this. So I'm actually just going to remove these controls and we're going to replace this with the draw distance. So in our terrain folder here, let's just get rid of the chunk size and replace this with draw distance. And set the step to 1. All right, so if I change this to 1, shrinks it down to 1 chunk. If I shrink it down to 0, or sorry, if I shrink it down to 1, we get our 9 chunks. If I shrink it down to 0, we just get that 1 chunk the player's on. And I can increase this all the way out to 3 chunks, 4 chunk draw distance. You can see it's getting pretty slow now. And 5 chunks. There we go. So if I start walking here, it's not terribly slow when we're loading this many chunks. You can see it's adding 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 chunks every time we're moving to a new chunk. But really, we can kind of tweak this number based on the performance of the machine that it's running on. That's one kind of cool thing about this technique. It's very scalable. If you're running on a really crappy computer, you can turn this way down, bring the fog way in, and it's still going to run nice. If you're on a beast of a computer, you can crank the draw distance way up and increase that fog to get that better visibility. So to asynchronously load our chunks, we're going to be using a browser API called requestIdleCallback. I'm in the MDN web docs right here, so let's take a quick look at what this does. And it's actually pretty simple. So this queues a function to be called during a browser's idle period. So we're constantly calling request animation frame. In between that, we want to be able to load those chunks so that we're loading chunks outside of the animation and doing it during the idle period. So the purpose of this, according to the docs, is to enable developers to perform background and low priority work on the main event loop without impacting latency critical events, such as keyword animation here. It's exactly what we're doing. Now there's some other documentation you can find on the background tasks API, which is what we're using here. And they talk about getting the most out of idle callbacks. So one key thing here is that you pretty much have an upper limit of 50 milliseconds to do the work in that idle callback. So we need to be able to generate a chunk in less than that amount of time. And in reality, you often have less time than that. So since we're kind of tied to that 50 millisecond amount, let's time how long it takes to generate a chunk right now. So I'm in our WorldChunk class. I'm in the generate method. Let's just use a timer here. So use the performance API here, get the current time. And then at the very bottom here, we'll log loaded chunk in. So we'll do performance.now minus start milliseconds. So let's go back into the browser. And we can see right away here, we loaded a chunk in 13 milliseconds, sometimes in 12, sometimes in 11. So let's try that with a bigger chunk size. So going back in our world class, let's bump the width up to, say, 64 blocks. And now by walking the direction here, you can see that was quite a bit of a stutter there. So this one took 77 milliseconds to load. This one took 60. So we're already going over that allotted time. There's going to be kind of a tuning process here of picking a chunk size that we can generate it within the allotted 50 milliseconds. So we'll stick with a 32 block width chunk for now, since we can load that pretty quickly. So to get started on this, at the top of our world, I'm going to add a new variable called Async Loading. We'll set that to true. This will be whether or not we want to load the chunks asynchronously. So let's hook it up to our UI. So at the top here, add a new property called, or that ties into our async loading property. Now back in our world class, let's locate our generate chunk method. So we're going to set this up to use that requestIdleCallback API. And what we're going to do is we're going to encapsulate the actual mesh generation into that. So not the entire chunk, but just this part here. So if this dot async loading, then load chunk asynchronously. Otherwise, we'll just call chunk.generate outright and just generate it on demand right then. Here, what we're going to do is we're going to call requestIdleCallback. So our callback here is going to be chunk.generate, but we need to bind this to the chunk so that this method is called in the correct context. It's called on this object. So we'll do bind to chunk. And then it's always a good idea to specify a timeout here. If you don't, things can get kind of funky. So I recommend, having a timeout. I put a timeout of 1 second here. So if it's kind of backed up and can't generate a chunk within 1,000 milliseconds, then it's just going to go ahead and generate the chunk. If you don't specify that timeout, sometimes it just won't load anything at all. So this asynchronous loading actually introduces an issue in that we're adding a chunk to the world before it could possibly be loaded. So that is actually going to cause some issues in getBlock here, because we might be getting a chunk that doesn't really exist yet. Or I should say that the data for the chunk doesn't exist. So the object exists. This will return true, and we'll try to get a block in that chunk, but there's no data to get, and it's going to throw an error. So what we're going to do on our world chunk in the constructor here, we're going to create a new property called loaded. We're going to set this to false. And then after the generate method has finished here, we'll set loaded to true. So we know that all of the chunk data has been loaded. All of the meshes have been generated. So we know that it's in its final state. So back in the world, when we're getting a block here, so not only do we want the chunk to exist, we want to make sure that the chunk is loaded. So this is chunk loaded. So in order to test this out, let's bump up our chunk size a bit, and we'll see how the loading performance changes. So let's also set the draw distance to 2. So we'll kind of stress this out a bit. So you can see we loaded a bunch of chunks here. And let's start by just disabling asynchronous chunk loading. And now when I walk to the next chunk, you can see we're getting some pretty bad stuttering. Let's go to the next one here. So you can see my screen freezes for probably like 200 to 300 milliseconds. Let's actually increase the magnitude here so it's a bit easier to see. And we'll bring the scale down a bit. So let's see how the performance changes when we enable asynchronous chunk loading. So now I'm going to walk in this direction here. So you can see that the stutter is now kind of spread out. So I'm no longer getting that really bad, like just hitching where it just lags for like 300 milliseconds. It's more kind of like a couple stutters in a row. So obviously I need to fine tune this a bit. The chunk size is probably too big. Need to make the chunk size smaller, but compared to what it was before without the asynchronous chunk loading, the performance is much, much better. And it gives us a little bit more headroom to work with in trying to maximize the draw distance. Now, another thing you might have noticed if you're an astute observer is that if you get to a certain point, the shadows are no longer visible. So I'm right on the edge here, and you can see that the shadows just stop. So we need to fix that. And that's actually quite easy to do that. All we need to do is in our animation loop, we need to update the position of our sun. So I'm going to move the sun outside of this function here so we can reference it in our animation loop. And then in our animation loop, then we want to update the position of the sun to the new position of the player. So for the sun's position, we're just going to copy the player position. So that puts the sun right on top of the player. Now we need to move the sun to its position relative to the player. So right now we're setting that position at 50, 50, 50. So what we need to do is subtract this from the player's position. So we'll do sun position, subtract. And then one other little nuance here is the target of our sun. We also need to update the position of that to the position of the player. So that way the sun is 50 units back in each axis away from the player, and that the target of the light is still pointing at the player itself. And I made a goof here. This should actually be negative 50. So we'll subtract this. I guess we could have just added 50, 50, 50, but whatever. And the last thing that we need to do, I read this in the documentation somewhere. Honestly, I can't remember where I read it, but we need to add the target of our sun to the scene as well. So now in our scene, as our player walks along here, you can see that the shadows are moving with me. So I can walk way over here, and you can see that we're getting shadows on these blocks. What we need to do is tweak the shadows a bit here, so I can still kind of see where the end of the shadows are. So we'll need to make the shadows a bit bigger. And I also think we should update our shadow map a bit. Right now, the quality's not super great, so I think we can improve that a little bit. So I'm going to set the shadow size here. So let's see, instead of 50, let's do 100. So I'm going to bump up our shadow map size to 2048 by 2048. And the last thing we need to do here is I need to update the far plane of our camera to 200. Just gives a bit more distance for how far those shadows will render. So now as we're walking around, I can't really see the end of where the shadows are. They're getting shadows really far in the distance there. I'm getting shadows on all these blocks. I think we need to tweak the bias a bit here. I'm still seeing right on the edges of these blocks. We're not getting that shadow. So what we can do is increase the bias a bit to 0.0001 negative. And that helped out the issue a little bit. So there's a lot of tweaking that you need to do to get the shadows just right, depending on the size of your shadow map, how big the shadow camera is. So it really depends on the settings that you're working with. All right, the final thing that we need to do here to tie all of this together is to add some fog to our scene. So we're not seeing the chunks popping in the distance. So we'll can do this really easily. All we need to do is scene, fog, set this to new fog. So for the fog color, let's go with the sky color. So that just blends in. And then let's set this distance. Let's see, the near distance to 50 and then the far distance to 100. So we'll add these values to the UI later, but we'll start with that. So now you can see everything kind of just fades off into that sky color in the distance. So now as I walk around, I also turned down the chunk size a bit so we're not getting that stuttering. So I can just walk and walk and walk. I guess you saw a chunk pop in over there. So we need to adjust the fog a bit, but I can just walk in this direction forever and I'd never know that chunks are popping in the distance. Obviously, you got to tweak the fog depending on how big your chunk size is, what your draw distance is, so you're not getting that pop-in effect. So let's wrap this video up by adding some UI controls for the fog. So we'll go to our UI class here. So we need to add one more argument here to pass in our scene and create a new scene folder. So we'll add a new control to control the fog here. So we'll set the near. So we need to make sure we go into main here. And when we're creating the UI, let's pass in the scene. So now I can be on our world here. And I can update this fog. So we can change this near value, go further out. Or we can bring it back in. And we can increase the far distance of the fog. So you see that's too far. I can see the edge of the world there. So we're going to make that somewhat of a lesser value. So you can set the near and the far distance really close together to get a bit of a tighter fall off in the fog. Or if you want something more gradual, you can set the near distance to something quite a bit smaller than the far distance. All right, so that is a wrap for this video. We have packed a ton into this video. I know that this infinite terrain generation, one of the longer videos in this series, but I think it's one of the most interesting. It's something that you can apply to a lot of other games where you're generating a dynamic world, a procedural world, and you need to somehow tune that to get the right performance for the player. So the next video in this series is going to be the terraforming. So we're actually going to be able to modify the terrain. We're going to be able to add blocks to it, remove blocks from it. You know, that's kind of the core of Minecraft, being able to modify the world and create whatever you want to. So really excited for that upcoming video. Please let me know in the comments below if you have any questions about this one, anything you run into. I do have a Discord, which is free. You'll find a link to that in the description below. So if you're working on this project on your own, you're running into some issues, just go to that Discord. We're building a great community there, and I'll be there to help you out as well. So be sure to check that out. So if you're enjoying this content and you want to see more stuff like this, please consider supporting the channel on Patreon. If you're a Patreon member, you get early access to these videos. You get voting rights on upcoming topics. It's a special members-only Discord channel. I'm continuously trying to think of cool perks for people that are supporting the channel. I really appreciate the support, so I want to provide as much value to you as I can, whether it be through these videos or fun extra perks. So thank you all so much for watching. If you want to be notified when the next video in the series comes out, be sure to subscribe to the channel so you can get a notification, get that video on your homepage. So until next time, take care, everyone. Thanks for watching.